Physics treats infinity as a practical tool for simplifying complex physical realities. If you have an electrically charged wire that never ends, how do you even begin to calculate the electric field surrounding it? Because the wire goes on forever, calculating its total charge is impossible. The value would be infinite. So we have to evaluate the charge differently. Instead of total charge, we use linear charge density, represented by the Greek letter lambda. This metric tells us exactly how much charge exists within a standard unit of length, say 1 meter. Lambda isolates the concentration of the charge. It frees us from needing to know the impossible infinite length of the entire wire. By redefining our measurement from total charge to charge per unit length, we establish the exact mathematical footing needed to analyze the space immediately surrounding the wire. To map the field, pick observation point P, a distance r away. Select 2 identical charge slivers, equidistant above and below it. Both emit diagonal field vectors toward P. These can be split into 2 perpendicular components, vertical and horizontal. Look at the vertical components. Because the segments are identical and equidistant, their vertical forces are equal but point in opposite directions. The upward push equals the downward push, so these vertical components perfectly cancel each other out. That leaves only the horizontal components. Since both point perfectly outward in the exact same direction, their forces compound and add together. Because our wire is infinite, every single point of charge along its length has a perfect matching twin on the opposite side. Every single vertical vector cancels out. The resulting electric field is purely radial, pointing strictly outward from the wire at a perpendicular angle. Proving the field is strictly radial allows us to bypass traditional, tedious calculus. We can instead use a mathematical shortcut known as Gauss's law. To use it, we must first define electric flux. Flux is a measure of how many electric field lines pierce straight through a given surface. Gauss's law states that the total electric flux escaping a closed, 3-dimensional boundary is directly proportional to the amount of charge trapped inside that boundary. Applying this requires us to invent an imaginary, completely closed 3D shape around a section of our wire. This is called a Gaussian surface. While Gauss's law holds true for any shape you can imagine, choosing the wrong geometry will make the resulting equations completely unsolvable. To calculate the field of our infinite wire, we need a Gaussian surface that perfectly matches the radial symmetry we just proved. A sphere is the most common Gaussian surface used for isolated point charges, so it is a natural starting point. Gauss's law requires field lines to pierce the shape's boundary at a perfect 90-degree angle everywhere. On our sphere, horizontal field lines hit perfectly at the equator, but slice through the poles at increasingly sharp, varying angles. Because the angle of intersection is constantly changing at every millimeter of the surface, calculating the total flux requires integrating across all those shifting variables. The sphere fights the natural geometry of the wire. It ruins our mathematical shortcut, forcing us to abandon it for a shape that respects the purely radial field. The solution is a right circular cylinder, positioned so it is perfectly centered, or coaxial, around the charged wire. We break the cylinder into 3 distinct geometric parts to analyze flux: top cap, bottom cap, and curved body. Focusing on the top cap, its normal vector points straight upward, while the wire's electric field points strictly outward horizontally. Field lines run parallel to the flat caps, sliding past without piercing, making their electric flux exactly 0. This leaves only the curved body, where the surface normal vector and the horizontal electric field point in the exact same direction. The field intersects the curved surface at a perfect 90-degree angle at all points. Because every point on this surface is identically distant from the wire, the magnitude of the electric field is a constant. By choosing a cylinder, we isolate all the flux to a single surface. We reduce a complex calculus integration into basic multiplication. Total flux simply equals the constant electric field multiplied by the area of the curved surface. To execute Gauss's law, we still need one final piece of data: exactly how much electrical charge is physically trapped inside our imaginary cylinder. We assign the variable L to represent the arbitrary length of our cylindrical Gaussian surface. We also bring back our metric from earlier, linear charge density, or lambda. The total enclosed charge is simply the charge density, lambda, multiplied by L, the specific length of the wire isolated inside our trap. We now have the defined geometric flux on one side and the algebraic enclosed charge on the other. It is time to equate them. Here is the final Gaussian equation. On the left side, we have our total flux, the electric field E, multiplied by 2 pi RL. On the right side, we replace the total enclosed charge with lambda times L divided by epsilon naught. The length variable, L, now appears on both sides of the equation. The length of the cylinder completely cancels itself. Rearranging the remaining terms to isolate E gives us our final answer, lambda divided by 2 pi epsilon naught R. The cancellation of L proves that the specific dimensions of the imaginary cylinder we drew did not matter. The electric field exists entirely independent of the mathematical trap we used to find it. This chart compares our new equation against the field of a standard point charge. A point charge's field weakens rapidly based on the square of the distance, but the infinite wires field weakens much slower based only on the direct distance, r. The wire maintains a stronger field over distance because as you move further away, your observation point is physically exposed to more and more of the wire's infinite length, partially compensating for the increased distance. Physically speaking, an infinite wire is an impossibility. Wires have ends, and the universe has limits. However, this infinite mathematics serves as a highly accurate approximation for the long, central sections of any real-world charged wire. The mathematical model only breaks down at the physical extremities of a real wire. At these extreme ends, the radial symmetry is destroyed, creating what physicists call end effects. By treating a wire as infinite, we bypass pages of tedious calculus. We utilize the precise geometry of a cylindrical Gaussian trap to uncover a basic rule of electromagnetism, a basic rule that continues to physically govern the complex circuitry and the massive city power grids we rely on every single day.